All right. Hello to everyone who watches the recording, and of course to everyone who is in the class. So today we are going to go next in our journey through basic control theory. And this time we're going towards one of the historically most important parts of control theory. It is something that fueled control theory from its inceptions. Hard to even say from which time, definitely from the middle of the 20th century until 80s, 90s. So like all this era of space exploration, of radio signals, electronics, commercial aircraft, all of this, which is a testament to practical use of control theory before modern computers. All of this was fueled by this, which is Laplace transform and transfer functions. Historically has been extremely important mathematical tool for using for doing control. So let me just, before we begin, let me just recap what we did before. So before, we looked at ODEs, especially linear ODEs, and we learned how to transform them into state space. And the difference between the two was that ODE is just a differential equation. It's just a mathematical object, very convenient. It allows you to see instantly how the variable of a differential equation, and we were looking at the scalar ODEs, so it is a single variable, like how it changes with time, and how its own derivatives influence its dynamics. Okay, so very clear. State space is a slightly different beast. On the first glance, it looks exactly like a system of first-order ODEs, and that is how we managed to transform normal ODE into state space. We transform ODE into a system of first-order ODEs, and then we call it state space, right? But on the second glance, state space is different because it gives you internal states X, inputs U, and outputs Y. So the difference is that now you have inputs U, which we will use to control the system, for example, and we have outputs Y, so things that we can either measure, or things that we can use in control, or things that we care about, those output signals. And then there are internal states. Notice ODE doesn't have internal states explicitly mentioned. Of course, they're exactly the same thing. It's the same object, but there is a difference, right? So today we are going to see the third way to represent systems. So ODEs, state space, those two ways we already know. Today we will see the third one. And same as ODEs are very convenient for a lot of things, same as state space is very convenient for a lot of things. This Laplace transform and transfer functions representation is going to be very good for a lot of things, right? I will mention the limitations and importance as we go. All right. So let us define first what Laplace transform is. So given a function f of t, function in time domain, so the function of time, okay, we can define its Laplace transform using this integral, okay. So the original function is being integrated like this. And notice there is this kernel of integration, e to the power minus s times t. The integration is done with respect to time. And you have this additional variable, which it turns out it is a complex variable, but We don't have to worry about it too much, but it is a complex variable. And as a result, t goes away, and we have a new function of s. Okay, this variable we call it Laplace variable. So this new function f is a function of Laplace variable. All right. This looks bizarre. When you see it first, it just looks like what happened. Hopefully you have seen it already on differential equations, so at least some of the shock is over. There is a convention, a number of conventions here. One convention is that we show the original function in small letters, function of time, whereas the Laplace transform is shown in capital letters. That is why, even though it is a scalar function, I show it in capital letters, but without making it bold. So it is italic, so, slanted, right? Same as any other variable. And it is uppercase. So uppercase can imply it is Laplace. And we like to, if we can, we like to keep this indication that it is a function of s, or so of Laplace variable. That is, convention, I guess. All right. So this is a Laplace transform. If you have seen Fourier transform before, you notice that this looks very similar to Fourier transform. The difference is this kernel is slightly different. For Fourier transform, the kernel here would be something like cosine omega t plus I sine omega t. If you think about it, what it would be is kind of like the same exponent, but with a purely complex power. So indeed, they are similar. A Laplace transform can be seen as a generalization of a Fourier transform. Okay. If you want an extremely abstract picture, Fourier transform is a transformation where you try to represent a function in this infinitely dimensional smooth basis, whereas the basis functions are sinusoids, so harmonical signals, so sinusoids of different frequencies. Okay, like Fourier series is, if you remember, representation of a function in a infinitely dimensional but discrete basis of frequencies with different amplitudes, right? You go cosine n, cosine t, cosine 2t, cosine 3t, etc. If I remember it. And the Fourier transform is infinite, kind of continuous spectrum. So you can take any frequency. There is no discrete jump within frequencies. And for discrete transform, you have to use integration like this. So for Fourier transform. Now, this is the same, but instead of sinusoids, which is, you can think of sinusoids as a steady-state solution to a differential equation, which happens to be stable, but not asymptotically stable, right? Marginally stable. Or you can think of sinusoid as, so, it's one way to think about sinusoid, right? Here you do it with over a family of functions, which is a solution to differential equations, which are anything. Can be asymptotically stable, can be marginally stable. So it includes sinusoids, right? But it includes also dwindling sinusoids. So sinusoids that go kind of like this, and they go almost to nothing. It includes everything. So it's just a more general. It allows to the sinusoids to die down, right? So this is, next step after Fourier. You can think about it this way. Right. What I said just now makes it sound like as if this is a deep math. You would have to go into Fouriers and here, right? But in fact, you'll see in the next slide just how easy the math becomes with this transformation. So let's just look at it. All right, scary integrals. Why not start with just transforming some functions. In fact, let's start with transforming this function, dx dt. You would think this is one of the craziest choices we could have made. As in, if you put let's say f of t equal to t here, you can kind of see what transformation would look like. Would not be pretty, but we can at least try. But here we propose, let's transform dx dt, so x dot. What's going to happen? Craziness. All right, let's just try. Let's just try and see how it looks. So this is how we often denote Fourier transform. We use L, Laplace transform. We say L of this function is something. So this means Laplace transform of a function. I use this math.cal font, math calligraphy, it stands for, I believe. Math calligraphy in LaTeX. So, suggest you do too. Using correct, specific fonts help for clarity. You don't have to use this exact same font, but it's just it's better than writing just L. Okay. Right. So we substitute the function here, dx dt. This is, remember, our kernel of integration. And everything else is kind of the same. Okay. How do we take this integral? We have dx divided by dt times dt. If we just get rid of this dt, I'm not sure if anything will make sense, because we still have to integrate over time. So, have to be careful here. So what we can do is perform integration by parts. Integration by parts. Remember, integration by parts looks like this. We say, if we have v times du dt integrate over dt, this is the same as u times v, okay, minus dv dt times u, okay, integration by parts. It's just a formula, I'm not going to derive it, is part of calculus, okay. Now, how can we use it? Well, we can recognize that du dt here, we can define it as dx dt. So this is our du dt, okay. What is our u is then, of course, x. What is our v? Well, this is our v, for example. Right, that's our v. And dv dt then would have to be derivative of this guy, which is minus s times e to the power minus st. Why is this derivative? Well, remember, the derivative of an exponent, ax, would be a times e ax. Okay. Just derivative of a nested function. You take derivative of the outer functions and derivative of the inner function. And inner function in this case is minus st. All right. So what do we get? We get that we get v minus u, v times u, okay, v times u, which is, let me just note, u, yeah, u is x, okay, and v is e to the power st. Okay. So this is this part. Right. Minus sign we get from here. And then we get our dv dt. Here is our dv dt times u again. Okay, so this is our integration by parts. Sounds scary, but not so scary. Right? Now, here is a key observation. This is our integration kernel. Okay. Here's our integral. And our those minus signs will cancel. So in fact, what we got is Laplace transform of new variable, of the new variable, which is this time x. Okay. So the new variable x. How do you denote it? So what we got is a Laplace transform of x plus this component. What this now let's look at this component now for a second. When we substitute 0 here, what we get is e to the power 0, which is 1, right? Okay. When substitute infinity here, what we get is the e to the power minus infinity, which is 0. So what we have here is 0 minus x times 1. So in fact, it is minus x 0. Okay. So this is just initial conditions. So Laplace transform of dx dt is initial conditions x to the point 0 plus Laplace transform. Well, let me just denote it. So Laplace transform of x of t is initial conditions of x plus Laplace transform of x times s. This is the most important part, times s. Where did this s come from? Yeah, here, by the way, I made a mistake. I should have been more careful. The kernel is just this guy. Let me. The kernel is just this guy, right? This most important detail, which I'm sorry I didn't highlight earlier, is this s here, which just pops out. Where did it pop out? Oh, here. Here's where it pop out. Right, and this s is getting here. So this is how we get s in front of this L. And we can get it out of the brackets because we integrate over t, we don't integrate over s. So it is just a constant part of under the integral. Okay. So what we get is Laplace transform of dx dt is initial conditions with a minus sign plus s times Laplace transform of t. Do you have questions about what we just did?
Why do you have minus in front of x of 0?
The way this notation works here is how should I put it? It is evaluate this function at the upper integration limit
Yeah,
minus function. Yeah. Okay. No, it's all this notation is very non-standard. So okay, good. So this is what we got. Now let's see where it leads us. Well, first, assuming that x of 0 is 0, which is a strange assumption to make, but the whole Laplace theory depends on using this assumption. So you have to take this assumption if you're going to use Laplace theory as in control, not in like differential equations. In control, we use this assumption. X of 0 is 0. Okay. Then we can denote L of x, so Laplace transform of x, as big S x of s. So we just say that Laplace transformation of x is big X of s. This is just a definition. Then we can obtain a differential operator. What is this differential operator? Well, it is Oh, it is saying that derivative of Laplace transform of a derivative is s times Laplace transform of x. So in fact, it is this derivative part becomes s, right? So Laplace transform of a derivative is Laplace transform of the function times s. And this is very nicely illustrated here. So Laplace transform of a derivative is s times x of s. So if we have a dot somewhere, it becomes s. That's all. That's all. That's all. Let's just see it in practice. It's going to be very easy. And this is possible because of this assumption. Let's look at the practice. Let us consider the following ODE, where U is input, right? The Laplace transform of U will be big U. Laplace transform of X will be big X. Now let's see how it's done. So first, this guy, X double dot. Let's begin with the left-hand side. So U becomes US. We don't know what U is. We just Laplace transform it into big US. Just sort of like this doesn't clarify anything. We just say that this was a function of time. This is now a function of s. Okay. Next, Laplace transformation of b times x. Well, it is b times x of s. So again, b is a constant term. It will always get out of the integration. So b just gets out. And x, the Laplace transform of x is x, just the uppercase letter. Okay. So far easy. A times x dot. Well, this becomes a times s times x of s. Because derivative operator, right? A again gets out. X dot becomes s times x. We just derived it. But you can think of it this way. You have x dot, the dot becomes s, the x becomes x, uppercase. Second derivative now. Second derivative of x, it becomes s squared x. Why? Well, you can imagine if we apply Laplace transform to the second order derivative, what will happen is something like this. So let me illustrate here. So L of ddx, I guess maybe let me try to do this. D of dx dt divided by t. I don't know. Is this understandable? Hopefully it is. Well, that is the same as s times Laplace transform of dx dt, right? How do I know? Well, because we said that the Laplace transform of a derivative of a function is just s times Laplace transform of a function, right? But this we already know what it is. This is just s times s Laplace transform of x. So this is how we get it. Laplace transform of a derivative of a function is the Laplace transform of a function times s. But this time the function itself is a derivative, so Laplace transform of it will again produce another s. So this is how we get those relations. So you can see for linear equations, the process is laughably simple. You just replace dots with s, that's all. And the reason why it is so simple is because we didn't try to actually put any real functions here. Like we didn't say u is equal to sine of t, for example. Because what would be Laplace transform of a sine of t? That is something we have to work out, okay? And if I say sine of t plus 1, again, have to work out for sine of t and for 1. What is it, Laplace transform? etc. For complex, complicated functions, this might be a huge headache. For sine of t, cosine of t, step function, etc., there are tables. So you can just look up what Laplace transform of any of those is. But we, for our purposes, will not need any of this. Now, before we move on, let me just state here what's going on with the math. What we did here, this transformation with arrows, is the extent of Laplace transformations that we're going to use in the course. We're not going to do the hard part, which would be, the hard part would be here. Let me denote it with a different color. Like this would have been the hard part if we knew what u was, okay? This would have been a hard part. Because u would be some function of time, which we would have to integrate, like actually do the actual math, which is more complicated than what we saw before, and get something explicit here. Okay, that would have been difficult. Then what people do in different courses, in courses on Laplace transform as part of differential equations, they solve this equation. Okay, they solve this equation in Laplace form, and then they transform the results into ODE. So this requires inverse Laplace transform, which is something that exists. It is its form is almost the same as Laplace transform. There's just I believe the power of E is different. So the kernel is different. So you can do that. And that is, you can imagine, pretty difficult because you would have some fractions there, etc. And but as a result, what you get is a solution to differential equations. Those two parts are difficult because they require working with arbitrary functions, and there is entire courses on how to do it. I mean, entire lectures, at least, how to do it. We're not going to do it. Why are we not going to do it? Because we know how to solve differential equations without Laplace transform. We can do it by calling ODE45, or we can use analytical methods such as matrix exponentials, etc. So we don't have to use Laplace transform to solve ODEs. It was popular in the middle of the century because back then matrix exponentials were not viable because we couldn't compute powers of matrices and SVD decompositions and other things that make it nice and easy to solve differential equations. Also, back then, solving with Runge-Kutta was too expensive. You didn't have computers, or your computers were slow. So instead of doing that, people were solving everything by hand. And by hand, Laplace transform, as difficult as it is infinitely simpler than Runge-Kutta. Okay. So back then, this was a viable method. Right now, we have better methods. We have computers, so we don't have to use Laplace transform to solve ODEs, and we're not going to. Okay, but historically, this is how things were done, and that is why a Laplace transform, even now, often taught as a how to solve differential equation kind of tool. And there's nothing bad in knowing how to use it for solving differential equations. It is just not something we do in control. Okay. Good. So this is just kind of like I wanted you to see the picture where the math becomes difficult and when it is easy. So we are doing the easy part, but there is a difficult part kind of like a step away. Okay. Now, let this out of the way. So this is the extent of the math we are going to do, like this transformation. It was very easy, I think. Now, what we can do is we can observe that we have a x of s on the left-hand side repeated, like it is in front of every term. We can take it out of the brackets, and we'll get something like x s squared plus as plus b times x of s equals to u of s, which we can express how x depends on u, and it would be this expression here. So what we have is x of s depends on u of s as 1 over s squared plus as plus b. Here, if you still think of s as differential operator, so if you think of s as derivative, basically indicating double dot, dot, no dots, then this becomes bizarre. Like this stops making any sense. It would be like 1 over derivative operator squared plus a times derivative operator plus what is this? But this is basically, if you don't want to think of it as Laplace variables, which I understand, for the longest time I didn't want to think about it as Laplace variables either. You can think of it as just a description, like a recipe for making differential equations. This bottom layer is how to distribute derivatives in the differential equation. This upper layer would be how to distribute derivatives in the input. Okay. So you can think about it as a recipe, but ultimately it is just a mathematical object. It's a Laplace function in Laplace variables. Now this form has a name. It's called transfer function. Why transfer? Well, because it transfers u into s. Like it is always in this form. You get u and you transform it into x. So that is what happens with this function. You get u, you transform it into x. Okay. Do we have any questions? You sure? We have time. Today we don't have a lot of slides, so ask away, please. This is complicated. It's perfectly normal to have questions here. In just this one slide, we went from ODE to Laplace transform ODE with differential operators and the Laplace transform essentially to transfer function representation. So it's very fast. It's very, very fast. Okay. So transfer function. So the transfer function set is the last representations that we're going to use in this course. We know already ODEs, we know already state space. This is the last one, transfer functions. Okay. Now let's just solve some examples to be able to appreciate what's going on. So given this ODE, 2x triple dot plus 5x dot minus 40x equals to 10u. How will the transfer function look like? Well, transfer function is what transforms x into u, right? So in front of you, there is a 10. So 10 goes here. Remember, what we're going to do is replace dots with s, and then get x out of the brackets, divide by what is in front of x. It will go to the denominator, okay? And this is the numerator. So 10 goes here. Now, what happens with 40? 40, unfortunate choice of color. Minus 40 gets here in front of coefficient with no s because no differentiation. What happens with 5? Well, 5 becomes 5s because of this dot here. We don't have x double dot, so we don't have s squared. Now 2x triple dot becomes 2s cubed. Okay. Questions about this one? No questions? Because this is a transfer function for this differential equation. Equivalent representation. Now, notice here I use x to u, right? That is, in my opinion, like unfortunate part about, at least, maybe it is unfortunate part about how I organize the slides. Maybe there is a better way. But basically, in transfer functions, you would have wanted to write y here, I guess. you would want to indicate this is an output. Because we are not talking about internal states here. Yeah, I mean, maybe this would have been better. Yeah, I mean, it's okay. Let's transform one more. In front of u, there is 1 here, so we have 1 here. Now we have 2x dot minus 4x, so it is going to only have 2 members. This minus 4x becomes this minus 4 here. And this 2x dot becomes 2s here. Very simple. And one more. Again, 1 in front of u becomes 1 here. This 4x plus 4x becomes plus 4. And this 3x triple dot becomes 3s cubed here. Okay. So this is a transfer function representation. As you can see, it is quite clear. There is very little here to stumble on. Change dots into Laplace variables, and everything here goes to denominator. Here it goes to numerator. That's it. Do you have a question? Okay. Now, let me show you how we can do something relatively interesting with something very relatively interesting with those functions. So we can take this equation where we have something quite strange here, namely this term, 10u dot. What is 10u dot? Why do we have u dot? Or is just kind of like strange, right? It's strange. There is actually nothing too strange about u dot being in the input, but we'll discuss it maybe tomorrow. Yeah, but we can easily transform it. And we transform it in this fashion. Let's do it step by step. So coefficient in front of y, in front of u, becomes, okay, we have a step by step here. So this becomes this, right? With a minus sign. This 10u dot becomes 10s times u again, the same u. This guy 2x becomes 2x. This guy 3x dot becomes 3s x of s. This guy 2x double dot becomes 2s squared x of s. And now what we get is these guys go to denominator. Here they are. They are in front of x. These guys would go to numerator. Here they are. And here is the denominator. When we divide everything by this part in the red, here's the denominator. So you can kind of see how it went, right? I mean, it is kind of so simple that I'm not even sure if we need all those diagrams, right? It's take this equation, replace dots with s, here s, here s squared, s, no s, no s, okay. Big small letters with capital letters. Isolate x on the right, left, u on the right. Then rewrite it as x times equals to some, expression of S times U of S. That's it. So this will be a transfer function that describes how U is transformed into X. Okay, so you get some input U. It is being transformed this way into X. So far, the question that you may ask is, what do you mean by transformed? And what I mean by transformed in the most simple terms would be this. You get some function, let's say sine of t. You find its Laplace image. That's what we call those functions, images. Sorry for introducing terminology midway. So we get Laplace image of this function. You multiply it by this guy. You get this huge function. You inverse Laplace transform it back into X, and you get your solution in time domain for this equation. This equation, I'm not sure if it scares you. I don't know exactly how it's, how I should put it. If I have to solve it, what I would prefer to do is to transfer it into state space, into first order ODE without U dot. And then I know how to solve it. I would just do Runge-Kutta or matrix exponential or anything like that. But this directly, I'm not sure how to solve it. It just looks strange. Of course, it would still work with various Runge-Kuttas, but you know, it just looks strange, is all what I'm saying. But with this, it doesn't matter. You transform it to the Laplace form, and from Laplace form, you go to solution, right? If we wanted to do it this way. That is what we mean by transformation. So the input signal would be transformed into output signal this way. By the way, if you know that U is equal to sine of X, then U of U dot is very clear. What it means it is just cosine of X or cosine of T. If U is sine of T, U dot is cosine of T. Right? So in this particular case, when we transform actual function, it again, even this becomes quite simple, right? Because you know what U is. All right. So this is how we can use transfer functions to deal with these types of equations. And as you can see, it is not a problem. At least transformation is easy. There's no barriers. Whereas in ODEs, this is just kind of looks weird. In transfer functions, it looks perfectly natural. Now, we can go to transfer functions from state space equations. That is also quite simple. How do you do it? Well, consider we have the standard state space equation. X dot equals to AX plus BU. U equals to C of X plus DU. Okay. How do we transform it into the state space? Well, of course, we could do it like carefully, step by step, but we can also do this like, I know, rush approach. I'm not sure if this approach is commendable, but it makes life extremely simple. We see X dot here. We know what derivative of X dot is going to be, what the Laplace transform of it is going to be. It is going to be S times X. Okay. In this case, I put I here just to, because we are going to use it the next. The S times X, that's essentially what it is. So Laplace transform of this guy will be this. I should have probably indicated that all of those become now Laplace variables. That maybe would have been better. But yeah, this is what I mean. This is now Laplace variables. We were discussing so far only scalar functions. And indeed, if this guy, let me use something else. If this guy is like one column, and if this guy is one row, and if this guy is a scalar, then this is a scalar case again. By the way, this du, we didn't see it very often, but this is, we call it feed through. This is like how U directly influences Y. We're not going to see it very often, but it can exist. Right. So if those are like one column, one row, and one scalar, then transfer function will be indeed a scalar. If it is something more, then transfer function will be a matrix. And those are not much more complicated than normal transfer functions, but they're not used either in practice actively nor in the literature, since they are not in the theory very often and not in practice very often. We don't have to think about them too much. So in all our examples, it will be scalar transfer functions. The whole transfer function theory is designed for seesaw systems. So seesaw systems with single input, single output, as opposed to MIMO systems with multiple inputs, multiple outputs. Okay, so transfer functions are mostly for seesaw systems. Okay, so for seesaw systems. All right. So here we didn't indicate anywhere that the thing is going to be somehow scalar, but in our practice it will be scalar. All right. Now let's find how x is determined on depends on u. How do we do it? Well, we get the x out of the brackets here. So what we get is si minus a times x equal to bu. Well, then we can, from that, we can go here by saying that x is then equal to si minus a inverse times bu. Okay, we just get it out of the brackets and then we multiply by inverse. This better exists. If this doesn't exist, then the transformation doesn't make any sense. So this should exist. Yeah, this should exist. For any of you interested in algebra, you can think of what S, in which cases S, this would become like degenerate, and you'll notice that it would become degenerate if S is maybe eigenvalue of the matrix A, etc. Right? Interesting things to think about. Yeah. So we have this. This is just a transfer function from u to x. But we want the transfer function usually from u to y, right? Not to x, especially since x is usually multiple variables. So x is almost never a scalar. Y can be a scalar. X, not really. All right. So how do we get from here to here? Well, we multiply x by c plus du. So what happens is we get, let me clear everything. We get this expression is being substituted here. This is what it is. Yeah. Then we have this part here. Right. And we have a u being pushed outside of the brackets. And that's what we get. This expression, this last formula, is basically a transfer function from u to y that we can get in state space. The derivation just requires one trick. Go from here to here, and then do algebra. This formula, you will see it often in textbooks, and it would look mysterious. It would be like c times I si minus a inverse times b plus d is, you look at it and you would think this is something like arcane knowledge, mysterious, requires deep study of control theory to understand. But what it requires is just a derivative trick, which you saw is, so basic it makes you suspicious. And it requires matrix manipulation, which you are, capable of doing very easily. So don't try to memorize the formula. Remember the trick. Then you can derive it on the fly. Okay. Like I don't memorize the formula. With D, for sure not. Like I don't remember where D goes, and I wouldn't try to go even if I remember this formula, I would derive it because you would make a mistake in the minus sign or something. It's not worth it. Just derive it each time. It's easier. All right. Do you have questions about that? This is how we are going to go from transfer function from state space to transfer functions. That's going to be, I think, on the homework, etc. Can you repeat how did we get x dot equals to six? Yeah, remember transfer functions, Laplace transform of a derivative function is equal to Laplace variable times Laplace transform of a function. Okay. All we did here is we did the same with the vector function. I is identity matrix. Identity matrix. What I mean is like diagonal matrix with ones on the diagonal. Okay. So this I doesn't do anything here. I could have deleted from this expression. It just is necessary here to indicate what we multiply by s. Did I answer your question, Ruslan? Okay, thank you. Thank you, Ruslan. All right. So this is what we get. All right. So you can see the process is simple. Now, let us just get some more useful terminology. You would think this course is all about terminology. You wouldn't be far from wrong from being true. So consider a linear ODE, linear D. We can represent it in three forms right now. This is ODE form. an times u to the power of n plus a n minus 1 times u to the power n minus 1, etc. plus all the way to a1 times y equals to bm times u to the power m plus etc. all the way to b1 times u. ODE. Okay. It can be represented as state space equation. Same exact ODE, but now as a state space equation. And now it can be represented as a transfer function. Okay. Okay. Now, instead of calling the system ODE or state space equation or transfer function, it is sometimes just more useful to call it a system. So sometimes we can use the word system. I just say it is a system G. We don't I want to denote it somehow. I don't want to denote it as transfer function, let's say, because maybe I ask you to find transfer function. Maybe I want to talk about the output of the system, but I don't want to talk specifically about the transfer function there, right? So instead of talking about representation, saying like, okay, we have ODE, or we have state space equation, state space model, that's what we call state space model, or we have a transfer function model, I would say we have a system. That is useful. And it is useful also because it reminds you that you can go from each of those to each of those. Okay? They are all interchangeable. Sometimes, of course, transfer function is for seesaw. This is for anything, for MIMO, for example. In fact, because I'm writing U bold and UY bold, I imply that this is a MIMO. So multiple input, multiple output. But I mostly do it to avoid ugliness with, how should I put it? The reason I'm writing this in bold is because this is the general case situation, right? But it is notationally this is not clean because it implies MIMO, while this kind of implies CISO. Okay, that is a problem here. However, if I try to write it correctly, what I will have here is a scalar, so something like this, right? Italic letter. This would have to be then a lowercase bold vector, which you are not going to see in any textbooks. So that's why I don't use it. And this would have to be either, this, it can be a matrix still, but more correctly, I guess, would be lowercase bold with transpose sign. This would have to be just a D like scalar. So the notation would be all over the place, wouldn't look like what you find in textbooks. That's why I'm not using those things. I'm sticking to this notation, which implies MIMO, but abusive notation, you can say. Right. Yep. So the system can be anything like this, can be this, can be this. Okay. And that is just a useful way to describe something. Okay. Good. Now, if the system G is stable, and stability notice is a property of the system, not of the representation. Stability is not a property of a transfer function or state space. It is just a system, right? So the system is stable, and you give it constant input u. So the input, again, exists outside of how you represent it, just input. Right? You give it input u, and the output of the system is then approaching some constant value y. Okay, so since the system is stable, it's not going to blow up. Although this is not something that we have proven, that stability implies boundedness. That's what we call this property, being bounded. So when you get input bounded, you get bounded output, right? We also didn't prove that stability implies that given a constant input, you get constant output. In fact, I'm not sure if you like asymptotic stability. Yeah, I guess it implies that. You need to be careful with those claims. But let's say that our system, given the constant input signal u0, gives us constant output signal u0, y0. We can call this pair of signals a steady state solution. So this pair of signals will be called a steady state solution. What do you mean steady state? Steady state means like state that kind of like goes steady. So stays the same. Okay. The ratio between u0 and y0 and u0 is called steady state gain. Steady state gain. So it is how much the system increases the signal. So just as an illustration, let me see if I can draw it. Let's say we have here our system. Here is the input signal. I will draw it in blue. Okay, the input signal is this. This is in blue. U is u equals to, let's say, equals to 1. Okay. Now the output, let's say, becomes something like, and here I apologize, I'll have to draw by hand, so it will be ugly. The output, let's say, is something like this, and it goes like this. Okay. The output is, let's say, y equals to 0.6. Okay. And this y is, it's not really equal to 0.6. It's kind of like tends towards 0.6, okay? Tends towards 0.6 as time goes to infinity. That's what we mean. Steady state solution is a solution at infinity, so towards infinity. Okay. So what we can ask ourselves is, what is the ratio between this and this? In this case, it is 0.6. It's clear. But we can compute it using transfer functions pretty generally. How do we do it? Well, the system G is represented as a transfer function. Our familiar b m s to the power m plus b1 an s to the power n plus a1. So we know that s is a derivative operator, right? So s stands in front of coefficients. When we go back to the differential equation, it would stand in front of like derivatives of u and derivative of y, right? It would be like, this would be, for example, a to an times y double y to the nth power, sorry, y to the nth derivative, right? And this would stand in front of y without derivatives. This would stand in front of the highest derivative of u. This would stand in front of u. But we know that it is steady state, so all derivatives are zero. That is what it implies by steady state. No derivatives. Okay, the derivatives are all zero. So in fact, what we do to find how the system becomes a steady state is we get rid of all of those, and we only keep b1 and a1. And that is just a scalar number. It's not a function. It's not a Laplace function. It doesn't have Laplace variables. There's just a game, like looking like this, which would say what is the ratio between the steady state solution and the input, steady input. So you can instantly see there are some ways to use transfer functions nicely. Of course, we could have done exactly the same trick with differential equations. There is nothing too specific to transfer functions here, but this makes it at least quite clear. Also, in state space, this would have been maybe just slightly more difficult. Just slightly more difficult, but not really difficult. All right. So this is what we can get almost for free using transfer functions. Just look at the last coefficients, and this is a steady state gain. Next time we'll see more what we can do with transfer functions. This was quite basic. We'll see more ideas next time. Second, let me just save this. All right. I assume we still have a little bit of time, right? Very little, but enough for us to finish. So last thing. Let's say we have a system described as a function, transfer function. So y is equal to x transformed by this function g of s. Okay. Notice I am being quite free with how I use those. Like there's y, there's x. Maybe it would have been better to use u here. The problem is, of course, the textbooks use things all over the place. So x is very typical here in this role. So you have to kind of allow yourself to see x as inputs as well. It's unfortunate. I don't know, maybe not. All right. So x is input in this case, y is output, and g of s is a transfer function. Now we want to modify the output of this system. We don't like this. Like we want to control it. Let's say it's unstable. We want to control it. So how do we control it? Well, instead of making x of s its input, we subtract from it the output. Let me use it. The output, but the output is modified by a controller. So we get the output of the function modified by controller and subtracted from input. This is called feedback. This is quite traditional way of thinking about it. You can imagine like electric circle where you have input going in. You have the system that runs on this input. Then you have the output going into amplifier, and the output is somehow tries to cancel some of the input. Quite typical arrangement. This also looks quite a bit like our u equals to minus kx. Indeed, you can think of it as if instead of x, this is our x, right? You can kind of think of it this way, as our state. This is our k. And goes, this minus is making us feel a little bit uncomfortable, right? This minus makes us a little bit uncomfortable. In fact, let me just quickly show you, this schematically. Maybe it will help. Next time we'll see it more clearly, right? So what we are trying to do is we have input. And yeah. And then we have this difference. After this difference, we would get, so this is input. Let's say it is x. After this input, we'll get something we call control error. Okay. Now here we have the system. This is what governs the what we care about, the system itself. Well, G. Right. Yeah, I guess we'll have to live with this rocket line. Okay. Here, what we have is this controller that we can propose. Okay, controller will be h of s. Small. And it goes back here with the minus sign. To indicate that there's a minus sign, we can make it black. Okay. So what happens? Our output, the thing that we want to control, is being multiplied by controller. And compared with the reference signal. X here is what we call a reference. Remember, we saw this last time as this name. So X is a reference, Y is output. We comparison, but Y is preliminary multiplied by this, transformed by this transfer function. Okay, and the difference is what gets into is what controls the plant, not the original system. The difference. Okay. And this is what we can try to do to implement our control. Previously, we remember what we tried to do is just say u equals to minus kx. So our closed loop system looked like the x dot equals to a minus b kx. So let me just write it down. Okay. Previously, what we said is dx dt, it will be equal to, this plus bu. Then we say u equals to minus kx. Therefore, the closed loop system looked like this. Okay, so this is what we saw previously. And you can see some similarities here, right? You can see some similarities here. is again something that loops back like the state is being multiplied by controller and goes with minus sign back into the action. Okay. But they do look different though. Like this is clearly not the same as this. All right. What I want to show you here is that we can deal with this situation. Like this looks kind of messy, but transfer functions have an easy and natural way to deal with those. Same as control had state space control had its own ways. Here, the ways to kind of like make it more reasonable looking. Like this, so far, it's just difficult to see what's going on. Why here? Why here? How it's going to operate. So the way it's going to operate is something like this. We have this function where we can open the brackets. We open the brackets, we get this expression in front of y, and here expression in front of y. We can transfer this expression to the left, and we get again y and y here, and we get x of s here, right? The same x. Then we can isolate 1 plus g times h on the left, g on the right, and then divide by 1 plus g times h. So we get, well, now let me clear everything. So we get this transfer function. This goes here, and this goes here. Okay. So we found closed loop transfer function. Here we found closed loop transfer function. This is it. This is a closed loop transfer function. This transfer function tells us instantly one thing, and this is the last thing we are going to discuss today. And that is that this denominator better never become 0. And it will become 0 when this guy becomes -1. And that is quite typical for transfer functions for the control loops of this type. It's quite typical for the control loops of this type. All right. That is it for the introduction of transfer functions. That's it for the introduction. Next time, what we are going to do is we will try to understand what kind of analysis we can do with transfer functions. They present one tool of analysis which is extremely important, that is Bode plots. And then we'll try to connect this type of control with the type of control that we did with state space. So far, it's a little bit difficult to see how this is related to state space. And we'll try to see it carefully next time. Do you have questions? That's it for the class. By the way, those recommendations, very good. So for self-study, it's very good material. Right. Do you have questions? If not, then let me thank you, and we'll see each other next week. Thank you, guys. Remember to go to the class, to the what do you call it, lab. Seminar is postponed, but the what do you call it, practical sessions aren't. Tutorials is postponed, but seminar is not. Okay, so make sure to attend the seminar. All right, bye-bye.